All right, folks, let's get down with the super technique. This new technique is called Simpson's rule, and the question is, what would be better than rectangles and trapezoids? And the answer is, if we could, on each one of these subintervals, have this rectangular base, but top it with something that is curved. If we could come through here and use some kind of curvature over the top of each one of these, that's relatively simple. We could do an even better approximation. So let's talk about how we're going to do that. The easiest or simplest curve we could use is degree 2, right? A linear. Degree 1 is a line. So we're not going to use trapezoids, which use lines. So let's use parabolas. So how is that going to work? Well, let's decompose this a little bit. And let's just take a look at maybe this little double subinterval in the middle. So let's deconstruct this. So let's say that we have, we have our curve, and this is x sub I minus 1. This is x sub I in the middle, and this is x sub I plus 1. And we have these heights at the end of it. Now we can, with 3 points, fit a parabolic curve, which will go through those relatively nicely. I can figure out how to make that look good. And we want to find the area here. So the question then becomes, what is this area total in this one region? Well, to do that, it'll be a lot easier if we shift this. So the area is not going to change. Let me duplicate this. If we take this region, duplicate, and we shift this to the origin. So instead of this being at x sub I minus 1, x sub I, and x sub x plus 1, let's make this the origin. Let's make this h to the right and negative h to the left, where here h is going to be the width of our subinterval delta x. But I'm just going to use h for an easier symbol to use in my calculations. So what do we know about this area? Well, this area in the middle is, using simple calculus, the integral from negative h to positive h of this parabola. Now, since this is a generic parabola, I don't really know what the coefficients a, b, and c are, but that's not going to really stop me from integrating it. So while I don't know what a, b, and c are, maybe we can find those later, but let's just talk about what this area is in terms of a, b, and c, and then relative to delta x, what we're calling h. So if we integrate that, that should be easy enough. This is a over 3 x cubed, plus b over 2x squared plus cx, and we're going to evaluate that from negative h to h. Now, I can't just cut this interval in half and double it because there's no guarantee that the right side and the left side are going to be symmetric there. So we'll have to evaluate this directly. And when we plug in the upper limit of h, we get a over 3h cubed plus b over 2h squared plus ch minus, when we plug in negative h, since this is a cube, it's going to be negative. We'll get negative a over 3h cubed. Since the next term is a square, we'll get positive b over 2h squared, and then minus ch. And if we collect like terms here, what we're going to see is these two cancel, and the other ones double up, so that this is 2/3 h cubed plus 2ch. And that's really the best we can do. I could clean this up a little bit, I guess. I could factor out whether they have a common factor of h. I'll pull out an h over 3, which will become a little bit more apparent why later. But let's just pull out an h over 3. That makes this 2. Whoops, I left out my a. Excuse me. 2a h cubed. So this is a 2a h squared plus 6c. It's not 6 strictly necessary, but I'm a stickler for algebra. So that's the area, but that's not going to do us any good unless we know apparently what a and c are. So what else can we do? Well, the other thing that we can do is try to fit this curve traditionally using a system of equations. This is the point h comma y value. This is the point 0 comma y value. And this is the point negative h comma y value. And since I don't know what those y values are, I'm just going to give them a name. We can call them f of x sub I minus 1, f of x sub I, or f of x sub I plus 1. But just for ease of calculation, I'm going to call this y naught, y1, and y2. Now actually, since this was shifted, y naught is really f of x sub I minus 1, the height there. But I'm just using y naught to approximate that. I could call it y sub I minus 1, but I don't want to be messing with all these subscripts, so I'll shift it back later when I'm done. Right now I just want to use 0, 1, and 2 for ease of calculation. So what do I know? Well, I know that we have the three ordered pairs, negative h y naught, 0 y1, and positive h y2. And I know that the function is unknown to me. F of x equals ax squared plus bx plus c. So I can solve for a, b, and c in terms of these heights, relative to these heights, if I plug this information in. That is to say, for negative h y naught, I know that y naught is equal to a h squared minus bh plus c. And at the point 0, y1, all I'm doing, by the way, is plugging in these ordered pairs, the inputs and the outputs, and I get y1 is equal to 0 plus c. So that one actually gave me c for free. C is y1, which seems pretty straightforward since that's the y-intercept anyway when shifted. And then h comma y2 is going to produce y2 is equal to a h squared plus bh plus c. So what can we do? Well, we're trying to solve for a, b, and c here, and one way to do that is to use elimination. So let's see what happens here. We already know what c is, but let's see if we can't eliminate b from this equation. So what I'm going to do is I'm going to call this, equation number 1, and I'm going to call this equation number 3. This is actually equation number 2. And what I'm going to do is I'm going to do something like equation number 1 plus equation number 3, which is y naught is equal to a h squared minus bh plus c. And y2 is equal to a h squared plus bh plus c. And what we're going to get here is y naught plus y2 is equal to 2 ah squared. These are going to cancel. And I get plus 2c. So let's see here. Remember from above that this was our area. Let's duplicate that and bring it down here. And it looks like we have a nice little common factor that we can substitute for. So 2ah squared is equal to y naught plus y2 minus 2c. Taking that information and substituting in, we get the area is equal to h over 3 y naught plus y2 minus 2c plus 6c, which is h over 3 y naught plus y2 plus 4c. But remember from equation 2, we know what c is in terms of our y values. So I'm going to rewrite this as h over 3 y naught plus 4y1 plus y2. And then finally, you'll recall that h is delta x, the thickness or the width of the interval. And this is a formula that will tell you what the area is under any parabola if you have 3 points of reference, where this is your y naught, this is your y1, this is your y2, and you have a nice little parabola connecting those. And if this is delta x, the thickness of one of those intervals, then this total area here is equal to this expression. So what we've just done is we've calculated the area under this curve that has a rectangular base but parabolic tops in pairs of two that allow us to interpret that area in terms of the heights alone. Now we can then interpret this as delta x over 3 f of x naught plus 4 f of x1 plus f of x2, since if this is y naught, this is x naught, and this is x1 and x2 correspondingly. So what? Well, let's go back up here. Now we have our general curve over a general interval, and now we're using not trapezoids, not rectangles, but these super sweet parabolic tops. So let's clean this up a little bit. Erase all this gibberish. Let's get rid of that. Let's get rid of that. Let's get rid of that. And all of that. Clean it up. Clean it up. Clean up your mess, Jenkins. Okay. So, what do we know? Well, each one of these has a thickness of delta x. And for this first triplet, we're going to use a parabola that passes through those 3 points. And so this area is delta x over 3 f of x naught, according to our formula, plus 4 times f of x1 plus f of x2. I better shrink this down a little bit and move it over. And then we'll move to our next pairing or triplet of values. And this is where they start to overlap. So in this interval, we're going to use the parabola that uses these 3 points. But you notice here that we're doubling up on x2. So this is going to be delta x over 3 times, this time, f of x2 plus 4 times the next one, which is going to be f of x3, plus a single f of x4, the next one on that end, which is over here somewhere. And then if I do one more of these, just for fun, right, I'm going to get another parabolic top that passes through these points, and then these guys double up. So then I'll get delta x over 3, f of x4 plus 4 times f of x5 plus f of x6. And this is going to continue, dot, 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 until I get to the end, which is delta x over 3 f of x sub n minus 2 plus 4 times f of x sub n minus 1 plus f of x sub n, as we go all the way out to the end. Now, if I consolidate this, what we're going to notice is all of these have a factor of delta x over 3 out front. So let's factor that out. And now we're going to have the following pattern. We have a single f of x naught. Then from our formula, it's going to be 4 times f of x1. Oops, I don't know why I have that in parentheses there. It's going to get messy. 4 times f of x1 from our formula. And then, not only do we have an f of x2 here, we have an f of x2 here. So it actually doubles up, because those are the two sides that butt up next to each other. And that's going to happen every time they butt up. So the pattern is going to be 1 of these, 4 of these, 2 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 of these, 4 of these, 1 of these on the end. So we have f of x2 plus 4 times f of x3 plus 2 times f of x4 plus dot, 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 all the way up to 4 of f of x n minus 1, the second to last term, plus a single f of x n. And that is our formula. And what you're going to notice is this. This is the pattern. So pay attention. The end values, x naught, the ends at x naught and x of n are used one time each. Then the odd terms are times 4. Oops. Well, I guess I didn't do enough even ones. But the even terms are times 2, and that's the pattern. So let's do a quick example, and then we'll be done with this section. And let's do something relatively easy to calculate. It doesn't need to always be an impossible integral. So let's do approximate the integral from 0 to 8 of 1 over x squared dx using n equals 8 and Simpson's rule. Well, again, it doesn't really matter what this curve looks like as long as you break up the interval accordingly. So here's 1, 2, 3, 4, 5, 6, 7, 8, 0, 4, 8. 1 over x gets pretty small. 1 over x looks like that. And we're going to be, oh, I don't want to do that. Sorry. Let's go 1 to 9. That way we don't have an undefined point. And so these are our subintervals. And delta x, which is b minus a over n in this particular case, is just going to be 9 minus 1 over 8, which is 8 over 8, which is 1. So that's pretty straightforward. And then x naught is going to be 1. x2 is going to be 2. Dot, 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 down to x sub 8, which is going to be 9. Which means that the area is delta x over 3 times f of 1 plus 4 times f of 2 plus 2 times f of 3 plus 4 times f of 4 plus 2 times f of 5 plus 4 times f of 6 plus 2 times f of 7 plus a single f of 8. Now, you might have heard me pause for a second as I did some thinking about whether or not I was contradicting myself, because up here I said it's the odd terms that are times 4 and the even terms which are times 2. But you'll notice here it's f of 2 times 4 and f of 4 times 4. But these are actually the odd terms because this is x0 and this is x1, x2. So just because this value in here is even doesn't mean it's not an odd term. So be careful there. Even value, but it is an odd term. Anyway, we should be able to crank this out. Delta x is 1. This is a 3. F of, so what are we doing? 1 over x squared. And this is 1 over 1 squared plus 4 over 2 squared plus 2 over 3 squared plus 4 over 4 squared plus 2 over 5 squared plus 4 over 6 squared plus 2 over 7 squared plus 1 over 8 squared for 1/3 times 1 plus 1 plus 2/9 plus 1/4 plus 2/25 plus 1/9 plus 2/49 plus 1/64. And what we get here, if we clean this up, is, let's see, 1/3, 2, plus, if I add these two together, I'm going to get 1/3. And then if I collect my fourths and my 64ths, this is 16/64, so this is plus 17/64, plus 2/25, plus 2/49. And if we get out our trusty calculator here, and we add that up, that's going to be 2 plus 1/3 plus, 17 divided by 64 plus 2 divided by 25. I'm narrating my calculator work here, so work along with me. Plus 2/49. I got about a total of, oh, that doesn't seem right at all. I hit a minus sign in there. Give me a second, folks. Here, let's clear this out and do this correctly. This is about 0.3 bar times 2.3 bar plus 17 divided by 64 is about 0.265625. 2 divided by 25 is 0.08. And 2 divided by 49 is about 0.0408116, and it doesn't look like it starts to repeat, so 0.816. We'll leave it at that, approximately. And so let's see, that plus 0.08 plus 0.265265 plus 2.3333333333 equals, I got about 2.719, and then I'm going to divide that by 3. And I got something in the neighborhood of 0.906 to the nearest thousandth place. Now we can check our accuracy because this particular integral was not beyond our capabilities. This is equal to negative x to the negative 1, evaluated between 1 and 9, which is apparently negative 1/9 minus negative 1, which is 1 minus 1/9, which is 8/9, which maybe everybody knows is approximately 0.8 bar, which is pretty close to 0.9. So this is an approximation, don't forget. And this is 0.8888888, so on and so forth. So we really only have an error of approximately 0.008 in the neighborhood there. That's pretty good for engineering, right? You're with 8/1000ths, so not too bad. Anyway, that's the idea behind Simpson's rule and the other approximating techniques. So make sure you guys learn those forms, and I'll see you guys in office hours. Get started on that homework.